Okay, so in this section, we're going to turn our attention to something called a rational expression. And basically what that's a fancy term for is a fraction, right? But now we're going to allow the numerator and the denominator of those fractions to be polynomials like we studied back in the previous section. So some examples would just be this guy where you have a linear factor in top and bottom, or you can have a constant over something squared, or you can have a whole mess of terms being multiplied in top and bottom. And what we'd like to do is be able to perform all the arithmetic operations on these types of expressions: add, subtract, multiply, and divide. Well, the only struggle here right off the bat is that you didn't encounter before, is that if you have fractions, you can't divide by 0, right? And so whatever number you have to put, whatever number you can put in for the variable to get a 0 on the bottom has to be discarded. You can't consider those values in the expression. We didn't face that problem with polynomials because we always looked at integer powers of x being added up, right? And so we didn't have that sort of issue. All right, so let's actually look at simplifying rational expressions right off the bat. Very first thing. So what we'll try to do each time is look at an example of fractions involving numbers first, and then we'll emulate that when we look at rational expressions involving variables. All right, and so for the first one, suppose we have a fraction that looked like this, right? What we mean by simplify is that the end result can't have any common factors in the top and the bottom, right? And so the way you simplify one of these guys is you can rewrite each of them as prime factors, a product of prime factors. So we know 16 is 4 2's being multiplied. 45 is 9 times 5, which you can write as 3 times 3 times 5. And then similarly in the bottom, 10 is 2 times 5, and then 48 can be written as 16 times 3, or 4 2's and be multiplied. Now, just group pairs of common factors in top and bottom and cancel them out. And the only thing that remains is a single 3 and a single 2. And so the end result, this product or this rational expression simplified, is just 3/2. All right, so we emulate that when you have a rational expression involving variables, right? But what does this rely on? It relies on kind of a result similar to one that we used with simplifying polynomials when you multiplied powers of the same base, right? So if you're dividing powers of the same base, suppose we have x squared over x cubed. We can rewrite x squared as x times x and x cubed as a product of 3x's. But remember, you can group pairs of factors common in top and bottom and cancel them. So if you do that, we're going to cancel 2 pairs of x's in top and bottom, and that gives you a 1 over x. But that whole process, notice if you compare this from beginning to end, you have x squared over x cubed. Basically, you have a 1 in the spot where you have the smaller power. And to get the power of the other guy, you simply subtract the bigger minus the smaller exponent. Right? So had this been x cubed over x squared, we would have had this flipped over. You'd still cancel 2 pairs of x's out, but then you'd have x over 1 instead, not 1 over x. All right, so for example, let's actually look at this guy. If you want to simplify a single rational expression, the first thing you have to do is factor the top and the bottom separately, right? So for this one, to factor the top, I'm going to first pull out a greatest common factor of 6x, and that gives us 6x times this binomial. The bottom is a product of monomials, so I can rewrite that as 4 times 6, and then I have 2x's being multiplied. Remember, the end goal here is to cancel out common factors. And so I don't need to further write the 6 as 2 times 3 and then each of those as products of primes, because we already observed there's a 6 there, right? So I can get rid of the 6. I can get rid of one of those x's. That's what I'm showing here. And what remains is just that whole binomial, x squared minus 2 in the top and the 4x down below, right? we know that this is simplified because there's no common factor in the top and bottom. All right, so that leads me to the following note, right? When it's this form, people have the incorrect tendency to say, I can get rid of one of these x's into the x squared, so they lop off one of those x's and then further kill that 2 under the 4. You cannot cancel that because those are not common factors, they're common terms, right? You have to cancel terms that are being multiplied in the top and bottom, right? Not being added or subtracted. And so I cannot, in order for us to get rid of this x down below, there had to have been an x on the 2 as well that we would have then yanked out, right? So you cannot perform this calculation. All right, so try these your terms for the moment, see what you get. Be careful with signs on some of these, right? Let's see what you get. All right, so for the first one, notice again, the idea is to factor the top and bottom and then cancel like factors. All right, so I'm going to rewrite the top as y minus 8 times y plus 8 using the difference of squares formula. And now you'll say, oh, I can get rid of the y minus 8 in the bottom. Not quite yet, because the terms are in the reverse order. And so what you have to do before you cancel that is pull out a -1 from one of them. Not both, but just one of them. I did it for the bottom just for simplicity, but you could have very well done that to the y minus 8. The minute you do that, you can cancel the y minus 8s, and then what you have is y plus 8 over -1. But remember that -1 can be put in front instead, right? The completely equivalent expression. All right. Number 2 is just really a direct consequence of using some knowledge of exponents, right? So what we do, we don't have exponent rules yet. We will in the next section, but just think about what these terms mean. -x to the 4th is really -x times -x times -x times -x. Right? You have 4 -1s being multiplied. Well, but if you have 4 -1s being multiplied, that just gives you +1. And then you have your 4 x's. And so -x to the 4th is the same as just x to the 4th. And then same way for the bottom here, 5x squared, quantity squared, that means 5x squared times 5x squared. Multiply the 5s, multiply the 2x squareds to get 25x to the 4th. The minute you do that, those two big chunks at the top and bottom cancel, leaving you with 1 over x. And then finally for the last one, if you want to factor each of those, again, they're trinomials, and so you factor using whichever technique you're more comfortable with trinomials. It turns out that once you factor them, they both have a z minus 3 in common, and so we're going to cancel those z minus 3s to get that fraction in the end. Okay, so that is what it means to simplify. Now let's go on to multiply and divide, right? I do this before adding and subtracting, unlike in the polynomial section, because it's easier technically. All we have to do here is, for multiplication, you just take factors that occur in top and bottom across the product and cancel them out. And for division, the first thing you do is you make it into a product by flipping over the fraction that follows the division sign, and then you do the same thing with canceling out like factors. So this is actually just like simplifying, only with more fractions. All right, so let's try the first one. If you were to rewrite each of these guys, every numerator and denominators of both fractions as prime factors, you would get this expression, and you can check that out, right? But now I'm going to clean up the bottom first. You have 2 cubed times 2 is really 2 to the 4th. Everything else just occurs once. And so I'm going to cancel out as many of the 2's and the 3's and the 5's as I possibly can in top and bottom. And turns out if I do that, the 2 to the 4th would go completely. I have only 1 3 left in the top and only 1 5 in the bottom. And so this product is equal to 3/5. Right? Remember here also, what makes this whole thing work is that the way you multiply fractions is by multiplying across the top and bottom. Right? And so the minute that's true, you have a single numerator and a single denominator here. And so when you write each one as products of prime factors, you can cancel technically across fractions because they really combine into a single one. And then, like I said here, to compute this quotient, all we're going to do is flip the second guy over, right? So we're going to multiply the first fraction by the reciprocal of the one after the division sign, and then do the whole process again, noticing that you'll get rid of the 3's and an 8 in top and bottom to get 5/8. All right, go ahead and try this. All right, so without actually me walking through it for the moment, you want to emulate the process above. And so the idea for each of these is to factor the top and bottom of each of these fractions in each cases, here being careful to then rewrite this as a product. But once you factor everything, cancel factors that occur in both top and bottom to simplify the result. See what you got. Okay, so for the first one, notice here, I can't factor the 8a to the 4th. It's a monomial, right? So it stays the way it is. This trinomial ends up factoring in this way. The 9 minus a squared is a difference of squares. Just be careful the order. Notice here the constant comes first, not the squared a. And so you get this product as a result. And then I could yank out a GCF of 12a from each of these two terms. That's where I'm getting this. Now what I would like to do is cancel like factors in top and bottom. Notice the 3 plus a and the a plus 3 are identical. There's no reason to yank a -1 out of those because there is no negative in between. Right? So these two, those two binomials are in fact the same, and so they get canceled out. However, the 5a minus 2 and the 2 minus 5a are almost the same, but again, the terms are in the reverse order, and so I'll yank out a negative, right, from the bottom one, let's say, and then I can cancel out those terms. The 3 minus a doesn't cancel with anything, so it just stays there. The 4 is common to both 8 and 12, so I can get rid of those. And then a single a is common up top, so I'll get rid of a single a. What then remains is a 2a cubed in the top and a minus 3 times a 3 minus a. This is your product in the end. This one is basically more of the same. Both of these are difference of squares. Both of these guys are GCFs, right? You pull out a common factor. And so what you get here is this fraction times that reciprocal. Okay? And so you rewrite each one as a product, cancel like factors to get this guy in the end. All right, I'm going to let you do your turn here. Just be careful, again, with orders of terms. And here, when you divide a fraction by a simple polynomial, remember you're going to multiply by its reciprocal, right? So just be careful with those. In the end, after, take a pause and then check these solutions yourself. I'll just put them up here for a brief moment. And then you can actually check those. Okay, for example 5, I'm just going to walk you through the general strategy here. So you have a quantity, a polynomial, divided by this entire term inside the brackets. And so what you want to first do, remember order of operations. You want to actually do whatever is in the brackets first, and then you do multiplication, division, left to right as it comes up. And so here, you want to factor everything in top and bottom of those two fractions inside the brackets. Noticing if I want to get rid of the x minus 3 here, I have to pull a -1 out. That's what I did there. And then I factored that trinomial. And so the minute I do that, I can get rid of those pairs of factors. Then what I have left over is this guy, which factored is equal to this, divided by what's inside the brackets. Okay? But that, remember what I'm going to do, I'm going to do the multiplication division left to right as it comes up. I can convert this over to multiplication by flipping it over, right? And so I get this product. Those 2x minus 5s are common to both, and so that -1 can then be put in front of here as a factor. So looking a little bit more complicated than the other ones because you have more than just two fractions being multiplied or divided, but that's where that order of operations kicks into play. And so if you take it one step at a time, they all resemble what you do up here, just have more steps to simplify the entire expression. All right. For complex fractions, let me actually come back to this because we have to talk about what does it even mean to subtract fractions. So we're going to come back to this momentarily. We just scroll down to this section here. All right, so how do you add or subtract fractions is the question. Well, two cases. If the fractions have the same denominator, you simply add or subtract the numerators like you normally would, and then at the end, you simplify that result. All right, so let's look at that, right? We looked at examples of fractions for which you did this. Here, they all have the same denominator 4, so I literally just add across the top. Then I have this fraction, right? And that fraction can be simplified because you can yank out a 2 from both. And so I just get 9/2. All right, let's look at, I'm going to not look at all of these. I'm going to look at the first and the third. Notice in each of these, though, all of the denominators are exactly the same. Don't let the fact here that I wrote them in the other order confuse you. Remember, multiplication is commutative, and so the bottoms here are exactly the same. So the general idea would be to just add or subtract across the tops, keeping the bottom the same each time, simplifying the numerator, and then seeing if you can cancel a like factor in the bottom and the top. Let's try that. So for the first one, if I add across, I get this expression. But then to simplify that, the only thing I have to first do is distribute that -1 through both terms. That's what I do here. And then gather like terms together. So I have a 4x plus a 2x minus a 3x. That's where that 3x is coming from. And then minus 45 minus 9 minus 1, well, that's minus 55. Right? There's your numerator. There's the denominator. You can't factor anything out of the numerator, and so there are no common factors to top and bottom, and so that is considered to be simplified. Okay. Let's jump down to number 3. Same idea. The denominators are the same, so I'm going to subtract across the top. To subtract these two guys, I'm going to distribute that negative sign through and then add like terms. Right? So I'm skipping a couple steps here only because we're now getting more and more used to this, but realize that's what you would have to do. You'd have to write down -2 plus x, gather your like terms, and then you get this guy. Notice that it's almost, 1 minus x is almost the same as the x minus 1. Again, the terms are in the wrong order, so I'm going to yank a -1 out, and then I'll cancel those like factors, giving me a -1 over x plus 2. Okay. All right, you can try this your turn on your own. Again, check yourself afterwards just to make sure you have it down, but it's exactly the same premise as the ones above. All right, what if the denominators are different, right? And so here, we know that when dealing with fractions, the most tedious part is getting the common denominator, the least common denominator actually, and then rewriting each of the fractions as equivalent ones with that denominator. That's where all the work is, because the minute the denominators are the same, you simply add or subtract the numerators as we did above, right? So the hard work is in getting this LCD. In the first one, what you want to do is find the smallest number into which all of them divide, right? And so for the first one, 16, 8, and 2, the LCD is just going to be 16, right? They're all powers of 2, so you want to take the highest power of 2 into which all of them go, and that gives you the LCD, right? And so what you do is you rewrite each of the fractions as a new fraction with that same denominator, an equivalent one. And so notice here, 5/8 is really 5 over 2 cubed. What would I have to multiply top and bottom by to get that denominator 16? I'd have to multiply by 2 in top and bottom. And so I'll do that. That gives me 10 over 2 to the 4th. So 10/16 is equivalent to 5/8. And then similarly here for 1/2, I need to multiply top and bottom by 8 to get an equivalent fraction. All right, and so what it turns out to be, this original expression is equivalent to this guy, right? So these are all fractions now with the same denominator. Remember, 2 to the 4th is just 16. So it looks different, but it really is just 16. Now they have the same bottom, add or subtract across the top, and then I get 5 over 2 to the 4th, which you wouldn't leave it like that. You actually rewrite this as 5/16. All right, that's a rather tame example of finding an LCD. The next one I'm not going to work through with you, but it kind of shows kind of the more misery that goes into finding an LCD in general, right? So if you have terms that look like that, it's not immediately apparent what the LCD is. And so I'll let you kind of work through that, but the premise is always the same, right? You always want to find the smallest number into which all of the denominators divide evenly. Right? All right, so how do you deal with rational expressions with different denominators? Right, so the idea, you want to factor all of the denominators as much as possible. Right? Then you list every factor that occurs in any denominator, right? So you have 4 fractions. If a factor occurs in any of those 4, you write it down as part of the LCD. And then you want to write down the largest exponent of that factor that ever occurs, right? So that means if that factor occurred in 2 different fractions, one of them had occurred once and one of them had occurred 4 times, let's say, then you include that factor to the 4th power as part of the LCD. You always use the factor with the highest power of any time that it occurs in any of the fractions. All right, and then you multiply all those guys together, that's the LCD. All right, so let's look at an example. All right, so let's actually compute this difference. Right. So first, the LCD, I already have the bottoms factored, so you don't have that extra step in this case. You want to include x, you want to include x minus 2, and you want to include x minus 1 in the LCD. Again, those are factors that occur in at least one, not both. They could be in both, but they have to occur in at least one of the fractions in the difference. All right, so our LCD is that product. Now, I want to rewrite each of these fractions, each of these rational expressions, as a equivalent one with the denominator equaling this LCD. All right, and so that's what I do here. I want to multiply the top and bottom of this fraction by what's not already in the LCD. Right, so here, if you compare its denominator to the LCD, note that x minus 1 is not already there. And so what I'm going to do is I'm going to multiply top and bottom by that particular factor. If I do that, I get 2 times x minus 1 over the bottom. Right, so this here, that whole product, will be an equivalent fraction to this guy, but now the denominator will be the LCD. Similarly here, I want to multiply top and bottom of this rational expression by what factor or factors is not already in its denominator. If you compare its denominator to this guy, what's not already there is x. And so I'm going to multiply top and bottom by x. All right, so notice here, both of these fractions now have the same denominator. In fact, that denominator is the LCD, right? So I can combine them into a single fraction with that denominator. I have the 2 times the x minus 1 from the first guy minus x times that factor here. Okay? And so now to simplify, right, what you do not want to do, I can't stress this enough, what you do not want to do is multiply out the factors in the bottom. Leave it in factored form, right? Nothing good comes of multiplying out the bottom. For the top, however, you do want to simplify the top. So I need to multiply through by that 2, through by this negative x. Remember, the negative comes through along with the x as part of the distribution. And then combine like terms. Okay? At this point here, if you were able to factor the top, you would do so, and then you would see if any like factors occurred in top and bottom. In this particular case, it turns out that the top doesn't factor, and so that is considered to be simplified. So, all right, go ahead and try these your turns. Again, on your own, this one is a little bit more complicated because there's 3 pieces and there's a lot more going on, I would say, right? And so, but try them and then compare your answers to the ones that I have posted in the video below. Okay, so there's the first one. LCD is t times t plus 2. So the only thing you need to do here is multiply the second fraction, top and bottom, by t plus 2, and then write as a single fraction and proceed. The second example is, like I said, it's slightly more complicated. The LCD, you take every factor that ever occurs in any of the denominators, namely x, x plus 1, and x plus 2. That product is the LCD. And now you need to multiply top and bottom of each fraction by what already is not in its bottom, that is in the LCD, right? So if you compare this guy, that whole bottom here, this bottom to the LCD, it's missing an x plus 2, and so I multiply top and bottom by x plus 2. Same way here, this one's only missing an x, and so I multiply top and bottom by x. But this guy here, the 3 over x, is missing 2 factors. It's missing x plus 1 and x plus 2, and so I have to multiply top and bottom of that fraction by both those guys, right? And so that's the only extra complication, is that what you're multiplying top and bottom by now is a quadratic in the end, and so the multiplication and the simplification gets a little bit worse. Not horribly worse, but just a little bit worse. All right. This one is similar. I'll let you read through that. And same way with your turn. So again, this is just more of the same. Let's go back to complex fractions. All right, so I'll have you look at those. Again, as I usually do, I have posted a bunch of supplementary videos if in fact you're getting more heartburn on this particular topic. So it wouldn't hurt to look through those if you're having struggles. All right, let me scroll back all the way. Reading backwards here to this. Okay, so simplifying what we call a complex fraction. All a complex fraction really means is a fraction within a fraction, right? And so here, notice we have a big bar, right? So we have a fraction, but the numerator and the denominator of that big fraction involve fractions themselves. But really, remember, we encountered this when we talked about properties of fractions back in the very first lesson. This is just a different notation for rewriting the top literally divided by the bottom, right? And so this really just means take that guy in parentheses and divide it by that guy in parentheses, right? So it really means this. In this form, it's not that big a deal, although we do have to worry about the order of operations when simplifying it, right? And so here, what you'd have to do is simplify what's inside the parentheses first, likewise here, but we already know how to do this from what we just talked about, right? You're subtracting 2 fractions here, and so you want to rewrite each of those as equivalent fractions with the LCD, which is 2 times x. In the same way here, the LCD is 4 times x, so you want to rewrite both those with that LCD. All right, and so that's exactly what I've done here. I skipped a couple steps again, as per usual, just because I wanted to cut to the chase once we get more used to this stuff. But I already converted each of these 2 fractions with that LCD, same way here. Combine them by subtracting the tops each time. That's from getting the 6 minus x and the 3. And then remember, though, if you're dividing a fraction by another, you change it into a product by flipping the one after the division sign over. Okay? Once you have that, you can get rid of common factors, which are basically a 2 and an x in top and bottom, and then just leave it like that. That's a perfectly simplified rational expression. All right. That's the normal way to do this. The other way is to keep the structure of the fraction intact. So I would prefer you, let's say, to do this, to get used to this, because it doesn't make it look like anything different whatsoever than you've already been doing, right? So I'd prefer you to approach it this way. But if you want to see an alternative approach, that will be used more in like the calculus and whatnot, then you can read through method 2 down below. All right, so let's look at this. I want you to try this your turn. Don't worry about 1. I mean, try it, but I'm not going to talk about 1 in the video. I'm only going to talk about 2 because this has a very particular form of what's called a difference quotient. And difference quotients, if you're going on to either business calculus or calculus for life sciences or the majors calculus or whatnot, in any of those, you're going to encounter this as part of what we call a derivative. And so simplifying things that look like this is really important for the beginning of that course. And so I'm going to harp on it somewhat in here. In any case, go ahead and try to simplify this and see what you get. All right, so let's look at that one. That's the first one. Here's the second one. And so notice I'm going to rewrite this guy as the top divided by the bottom, which is h. I'm not going to worry about that dividing by h until the very end, right? So just keep tacking it on, but I'm not going to worry about what to do with it until a little bit later. To simplify this difference, I want to get an LCD, right? But the LCD is the product of all factors that ever occur in any of the bottoms and the highest power of each of those factors. Well, we have an x squared and we have an x plus h quantity squared. They have nothing in common. They're distinct factors. And so the LCD happens to be the product of both those terms. All right, so what does that mean? Well, it means to simplify this, I need to multiply this guy by x squared over x squared in order to get the LCD down below. And then I need to multiply the top and bottom of this guy by x plus h squared. Again, the whole point of doing this is to get the LCD down below. Notice that both of these fractions have the same denominator, and so the minute that's true, I can simply subtract across the top and put it over that LCD. Now there's still a little bit of work to do before we divide by the h. Remember, you do not multiply out the bottom. No good comes of that. But you do have to multiply and simplify the top because you want to cancel as much as possible out of there with the hope of then factoring it and then getting rid of even more. Right? So what we have to do, you need to multiply out the x plus h squared. Remember, you're foiling that. It's really x plus h times x plus h. That gives us x squared plus 2hx plus h squared. But I'm subtracting that. And so you notice here I have negatives in front of each of those terms because I have to distribute that negative sign through all three terms. Once I've done that, notice the x squareds cancel. And I could yank out a negative h from what remains, right? These two terms went, right? The x squared terms went out. Those went. But I could yank a negative h out. All right, so I've done that. And then once I've simplified that, I'm going to rewrite this as a product so that I could cancel even more. Remember, dividing by h is the same as multiplying by 1 over h. And once I've done that, this h and this h go. That leaves me with just negative 1 times the 2x plus h and that entire part of that LCD here. That's as far as you can go, right? You cannot get rid of this h with this h because they're not factors, they're terms. They're not being multiplied, they're being added in the top and bottom. Right? So this is considered to be simplified. Okay, so go back now to the homework, right? Go through, make sure before you attempt the homework problems, you go through the your turns that we did not talk about, check your answers, make sure you're comfortable, and if you're not 100% comfortable with the material, view those supplementary videos that I posted on that additional list before delving into these homework problems. Because if you just delve into the problems and are not comfortable, you're just going to keep making the same errors over and over again. All right, then let me know how this goes.